We are still in section 6.3. So this first topic is just introducing another format for component form. So it tells you that the standard unit vectors are I equals 1, 0 in component form. This has only an x component, so it's like the x unit vector. J equals 0, 1, which makes this the y component. Okay, so if vector w equals 7, 11 in component form, then this can be written as a linear combination of the unit vectors I and j as 7i plus 11j, where the I is representing the x component and the j indicates the 11 is the y component. So all this is saying that if I have in component form 3, -5, I could also express that as 3i minus 5j. These are exactly equivalent forms and they're interchangeable. So the same is true for this other one. If it's expressed in linear combination form as -i plus 2j, it's really saying that the x component with the angle brackets is -1, the y component is 2. Okay, and they will interchange the notation, and I will also interchange the notation. So for example 5, it says, let u be the vector with initial points 8, -5, and terminal point 3, 1. Write u as a linear combination of the standard vectors, unit vectors I and j. So they want me to find component form, but they want to express it in terms of I and j. So just like we did previously, I'm going to do it in component form first and then switch it. You don't have to do this. I really prefer component form. So in component form, it's terminal x minus initial x. And I would not show this step except it's your notes. Terminal y minus initial y, 1 plus 5. So -5, 6, this is component form, okay, which is a great format and it's very useful. But because they specifically asked me to write it as a linear combination of the unit vectors I and j, I'm rewriting it as -5i plus 6j, even though this is the exact same thing. If you're doing WebAssign, you may need to pick I and j from the menu of symbols because I don't think the normal I and j works. Okay, the next topic they're going to introduce is direction angles. So in this case, they say if u is a unit vector with a direction angle. When they say direction angle theta, this is consistent with how we did angles on the unit circle, where the positive x-axis represents 0 and the positive direction is counterclockwise. Okay, so I'm just going to sketch a picture of vector u. Vector u, let's just hypothetically say it's right here. And that would make the terminal point x, y, because the component form is x, y. Okay, this is my direction angle. Okay, if this was on the unit circle, the x component would be cosine theta, the y component would be sine theta. Or if I express this in terms of the unit vectors, I might say that this is cosine theta times I plus sine theta times j. And this is assuming this is a unit vector where the radius or the size of the vector is 1. Okay, typically the magnitude of the vector is not 1, so we're going to generalize these formulas just like we did for the unit circle. So in this case, it's saying let v equal ai plus bj, or in component form a comma b with the vector, the direction angle of theta. If we want to rewrite this in what they call component form, or x component, y component form, the way I could calculate that is the x component would be the magnitude of the vector times the cosine of theta, and then the magnitude of the vector times the sine of theta. This is just like when we did r cosine theta and r sine theta. R is the radius, which is similar to the magnitude, and this is called component form. Okay, if I'm given the component form and I want to find the direction angle, I would say that the tangent of theta is going to equal to b over a, which is very similar to y over x because it's the y component over the x component. And this would give me the direction angle but for it to be called a direction angle, it does have to start from the positive x-axis. And we typically give it as a positive format. Okay, so for example 6, I'm just going to find the direction angle of each of these vectors because the direction and size is what matters for vectors. Okay, and that is supposed to say v equals negative 4i plus 4 root 3 times j. I will change that. Okay, remember this is the x component and the y component. So if the x is negative and the y is positive, I'm thinking of quadrant 2. So keep that in mind when I find my angle. Okay, if I want to find the direction angle, tangent theta equals the y component over the x component, which I will simplify to negative root 3. Okay, let me think about this. Okay, if the tangent's negative root 3, I'm kind of thinking of this point or this point. Okay, because I need to be in quadrant 2, I actually want this point right here, and I want to give my answer positive, starting from the positive x-axis. So that's 90 degrees plus 30 more degrees. So I'm going to say that that is theta equals 120 degrees. Okay, now if you're a calculator person, because we are using calculators, if you use your calculator on this, if you recall, the domain of arctangent is negative 90 degrees to positive 90 degrees. If you use your calculator and do the inverse tangent of negative root 3, it's going to give you the answer negative 60 degrees, because that's within the range of arctangent. Because negative 60 degrees is in the wrong quadrant, to get the answer in the correct quadrant, I could add 180 degrees to this, and it will give me the 120 degrees next that way. So either way you would like to do it is fine. If you're using a calculator, though, remember if it's in the wrong quadrant, add or subtract 180 degrees until you end up in the correct quadrant. Okay, so for B, it says minus 10j. So this is a negative x component and a negative y component, which puts it in quadrant 3. Okay, so the tangent of theta equals y over x. Okay, this is not a unit circle location, so I'm going to use the inverse tangent on my calculator to figure out the answer. Okay, so let's see. I got 73.3 degrees according to my calculator. Let me just check the quadrants on this. Okay, you don't have to draw a picture, but just keep this in mind. Say 73.3 degrees is around here. But my vector is actually in quadrant 3, so I'm looking for the answer that's on the opposite side of the circle. If my vector had been in quadrant 1, that would have been a perfectly good answer. But because my vector is in quadrant 3, I want to find the other answer. So I'm going to add 180 degrees, and I will get 253.3 degrees, which is consistent with the third quadrant, so that must be a more correct direction angle. Equals negative 3i. Okay, so for example 7, I'm going to try to find the component form of vector v with a magnitude of 5/2 and a direction angle of 210 degrees. Okay, and remember, if I want to find component form, I could use the I or the j. I prefer these brackets because it's easier. I'm going to do the magnitude times the cosine of the direction angle, comma, the magnitude times the sine of the direction angle. And just think cosine is x, sine is y, just like on the unit circle. If those angles were not convenient on the unit circle, or if they told me to round it, I would use a calculator or I would leave it like that. But these are actually, I know this is on the unit circle. This is 180, so 210 is going to be right here, which is negative root 3 over 2 comma negative 1/2. Okay, so I'm really saying this is 5/2 times the cosine of 210, so times negative root 3 over 2, comma 5/2 times the sine of 210, which is negative 1/2. Okay, and then I am going to simplify this a little bit. Since it's a unit circle point, I can get a nicer answer. So negative 5 root 3 over 4 component form, comma, negative 5 over 4 component form. V equals, and if I look at my component form, since it's negative, negative, it should be in quadrant 3, and my direction angle told me it was in quadrant 3, so that matches up and that's consistent. Okay, example 8 is, we're going to put it in component form, but it's kind of like a word problem. Not really. Okay, so it's asking me to find the component form, which is exactly what I just did in the previous problem. They're telling me the velocity of an airplane descending at a speed of 135 miles per hour, angle 25 degrees below the horizontal, and then they put theta equals 205 degrees. Okay, in this case, they want it to represent the velocity. So this 135 miles per hour is going to be my magnitude of the airplane. I would not need a picture, but I'll sketch a picture so you can see. Since they told me theta is 205 degrees, that's my direction angle. Okay, and they said it's 25 degrees below the horizontal because it is, but it's below the 180 degree line for the horizontal, and the magnitude is 135. So the vector of the airplane, what do I call him? I'll call him A, is going to be the magnitude times the cosine of 205 degrees, and the magnitude times the sine. Okay, if they ask for it in exact form, I would leave it like this because that's not a known point for me. But often on these, they're going to ask you to put it in your calculator to get an approximation. So I'm going to put each of those in my calculator. Pay attention to what they tell you to round it to. Okay, so this is what I got as my resulting component form. This is component form. Component form always has an X and a Y. So that's what they want. I could use the I or the J and the J, or I could use the angle brackets depending on what they ask for. And if you want to check and see if it kind of makes sense, 205 degrees is over here. That's in quadrant 1, 2, 3. If I do negative X, negative Y, that's also in quadrant 3. So this is consistent with the given problem. Okay, we're going to do one last example to start getting introduced to applications, which is what we will be doing more of in the future. Okay, so we often use vectors when there's more than one force acting on an object or acting on each other. So for example 9, it says two forces with magnitudes of 80 pounds and 50 pounds act on an object at an angle of 30 degrees and 75 degrees respectively. Find the direction and magnitude of the resultant of these forces. Okay, now when you're adding forces and things like this, we want them in component form. Okay, there's two forces. Let me give one of them, I'll call one of them A. I'll call the other one B just because it's easier for me to label things. Okay, I'm going to first rewrite each one in component form because it's easier to work with in component form. So the magnitude of force A is 80. The angle is 30. Okay, depending on your calculator skills, you might leave it like that for now, or you might want to convert it to a decimal right now. It's completely up to you. You could leave it in the first format, or you can decimal it now, depending on what's more convenient for you later. Okay, I'm going to do the same for force B. What is the angle? The angle is 75 degrees, and I'm assuming that's a direction angle. Okay, and again, you can leave it in this format if that's how you plan to work with it. If your calculator, it's more convenient to change it to a decimal now, you could change it to a decimal now. That's up to you. Okay, now what are they asking for next? Okay, the two forces are acting on an object together. So I want to see together what are they doing. So I'm going to add them together. But with vectors, you can only add them together when they are in component form. So I'm going to add the x components and the y components up. Now, depending on your calculator again, you might just take this expression, add it to this expression to get the new x component, or you might need to do the decimals and add the decimals together. Okay, but for my x component, I get 82.22. Okay, and then if I add up the y components, 40 plus 48.30, I get 88.30. Or you could add 80 sine 30 plus 50 sine 75 degrees, depending on the calculator again. Okay, this component form represents the resultant vector. If they asked me for the component form of the resultant vector, I would be done. But they didn't ask me for that. Okay, what did they ask me for? They're asking me for the direction and the magnitude of the resultant of these forces. Okay, so I have the resultant vector. I need to find the magnitude and the direction angle of those. Okay, let's do the direction angle first, just because it asked. Okay, direction angle, y component over x component. Okay, I definitely, not on the unit circle calculator, this thing. Okay, I used inverse tangent of that expression. I got about 47.04 degrees. That's in quadrant 1. Is my resultant vector in quadrant 1? This is also in quadrant 1, so that's consistent, and that is a good answer. So this is my direction angle. Okay, now they want the magnitude of my resultant force. The resultant was when I added the vectors together. Okay, so I'm going to use the component form. Remember, it's the x component squared plus the y component squared and then square root it. Okay, put that all in your calculator. I got about 120.65 pounds. Okay, and this is the magnitude of the resultant force, which is the magnitude of those two vectors working together. Should I sketch it? I'm going to sketch a picture. You don't need to sketch a picture. I'm just going to show the visual people what's going on here. Okay, let me draw this little guy. Okay, where A is 80 sine 30. So he's somewhere out here. That's A. Where's B? B is 50 cosine 75 degrees. So it's 75 degrees. He's going 50. So he's a little shorter, but he's going up here somewhere. Okay, if I do A plus B, I'm basically just starting with either of these. Let's say I start with A. I'm going to add B to the end of it. Okay, so A plus B is actually starting from here and going all the way to here. It normally makes a little parallelogram. Okay, so if you look at that new resultant vector, in this case, it looks longer than A and B, which makes sense because I got 120.65, which is bigger than the 80 or the 50. The angle could be 47 degrees. That seems reasonable given where A and B are. So you don't need to draw a picture, but for visual people, it helps. Sometimes it can help you see if your answer seems reasonable.